Okay, hello everyone. Thank you for joining us on this webinar together with ESBE. The plan is to have around 40-45 minutes of education, and then there will be a short quiz at the end. Let's go on the next slide just to start going. My name is Mario Dodić. I'm heat pump trainer and founder of HVAC Education Hub. Regarding content, idea is to have two main sections. First part will be mine, around 20 minutes, regarding heat loss, delta T capacity flow rate, so everything related to heat pump, and water volume and flow rate. Second part will be from Nigel from ESBE UK. He will explain what are the main components of heat pump system, what is the difference between diverting and mixing valves, and how to size a valve and what is important. At the end, there will be a quiz, 8 questions, and 5 minutes is time needed, so maximum time. And first 5 people, so with the top answers, will receive some prizes from ESBE. So try to follow up. Everything will be related to what we are talking today. I want to start with this and with a question: less is more. Usually, we are trying to overcomplicating everything because we think that it will make things better. This is one family house, and you can see here that tens of thousands of euro of equipment, and they are spending 1,000 euro per month on heating. Cooling was not working. Just for introduction, because we want to make things simple. And the main idea, you can see here how many valves, pumps, and everything. The main idea is to move water from point A to point B without unnecessary mixing, losing, and so on. So this is what we are paying for. We are paying here, and if we are losing something there, we will not have efficiency. So just for start, one picture. And usually what I can see, that most of the houses are with more equipment than needed. Just to start with some basics, because we have really a wide audience from experts to beginners. We need to define what is the heat source and what is the heat sink. So generally, heat source is something from which we are transferring the heat. For example, gas boiler, because we are burning fuel inside. And heat sink is the system to which heat from another system is transferred. For example, radiator. Here you can put heat pump, wood, pellets, whatever. But the main thing is that this is point A, and we need to move this water to point B. If we want 20 degrees in our room, this is only the one part of the input information. Everything else, what we are paying is here. So we are paying here on the source of the system. So remember, source and sink. We are moving heat from source to sink. Next part, I will not go in details, but generally, what is heat loss? Also, with you can oversize the system, undersize the system, but generally, even the best house is like a bucket full of water, and this bucket is leaky. So our walls, windows, doors, depending how good are they are leaky, and there is always something leaking from our house. And what is our job? Our job is to fill the bucket in ideal world exactly how we are losing that heat or that water. So the most efficient system will push the heat at the exactly same rate that what we are losing here. We can do that also with gas boilers, with heat pumps. Previously, with old technologies, we are pushing too high temperatures because we cannot lower the temperature. And then we have thermostats and other regulational elements. But today with heat pumps and with gas condensing boilers, we can make this really effective. Just also one comparison how to make this effective. If we use Here we have wide audience. In some places, for example, in Croatia where I live, you can have -15 design outdoor temperature. In the UK, -2, -1, -3, depending where you are. But just for understanding, on -15, some house, average house, with 5 kilowatt heat loss, the same house on +10, so when outdoor is +10 or +5, let's say most of the heating season, it's only 1.5 kilowatt or 2 kilowatt at 5 degrees. So if we are pushing this 5 kilowatt, what we need to design all the time, we are losing the energy and efficiency here. This is why outdoor temperature, weather compensation, and so on, this is important. So we can really, this bucket, if we remember the bucket from the last slide, we can really push the heat what is needed at that point. Another important topic, probably the most important topic with every heating system, every hydronic system, is difference between temperature and difference between flow rate. Here you will see example with 9 kilowatt gas boiler. Gas boilers, they are working usually with delta T20, could be also 10, 15, but generally old boilers with delta T20. It means that we are pushing, for example, 52.5 degrees flow temperature to have 42.5 in our radiator and to have return 32.5. So this is delta T of 20. We are pushing the heat with temperature difference of 20 degrees. And our flow rate here is 6 liters per minute. So 9 kilowatt gas boiler with delta T20 has 6 liters per minute flow rate. If we use the same 42.5 degrees, but now with heat pump, we will have delta T of 5. We are pushing 45 degrees and we are returning 40 degrees. So the same 42.5, what we want in our radiators, but with quarter delta T. So let's say here we have 4 times higher delta T. And what will this affect? This will affect our flow rate. So here you can see 6 liters per minute, and here you can see 24 liters per minute. This is 4 times bigger. So delta T is 4 times, let's say 4 times lower or quarter of this, and flow rate is 4 times bigger. If we have double delta T, our flow rate is half. So imagine these numbers, how much times we are increasing delta T, we need to decrease flow rate and vice versa. So we need to push much harder this water through our pipes and through our radiators. And to not go deep in formula, here is one, let's say, quick formula for delta T5 and for heat pumps. If you want to calculate your flow rate in liters per minute, you need to multiply your heating capacity with 3. So for example, you have 20 kilowatts, so some big system, you know that you need roughly 60 liters per minute to have delta T5. It is really important to remember that this delta T5, it's, let's say, theoretical value. So it will depend, Nigel will explain later on also something. It is related to our system. So if our system is like on the picture from the beginning, we'll probably not have delta T5. So this is theoretical value, and this is what our heat pump will try to achieve. So just remember this, I say it's fast formula. If you have a lower flow rate than needed, then your delta T will probably be higher. Just if you are on site or somewhere, you can calculate from head. And we explained, just to put the focus here, so 4 times higher flow rate. And what is the main thing? If we have our pipes and we are pushing the water, you can see the difference between bigger pipe and smaller pipe. So here we can we are pushing the water much harder than here. So this is one of the main issue with if we are converting from old systems with delta T20 to new systems. Why is this important? Because we want to have our velocity between 0.5 and 1.5 meters per second. What is velocity? Velocity is what you can see here. So how much meters per 1 second our water is moving. If we are here, let's say under 0.5, it will not be a big issue, but if we are above 1.5, more pressure drop, more noise, less efficient system. So we want to keep everything, let's say, in ideal world, like 1 meters per second. So not to go above that.
There's also a danger of erosion if you go above 1.5 meters a second, so the system can become damaged.
Yes, Nigel, you have more experience with the pipes and this kind of a thing. This is probably the issue. I assume probably not, let's say not big issue if you have 1 meter of pipe and if you are designing for some really low temperature and you cannot change this. I assume this is fine. But generally, if you have more than that in system, you need to check calculations and try to keep things. What is sometimes you cannot change the pipe. And it's important then to check other elements, what we will mention later on. And between these elements, you can play and you can choose what is the best for your system. So maybe one valve or one pump will make this difference for erosion, noise, and other things what we don't need and want in our heating system. And the main part, we say we are pushing the water. How are we pushing water? With pumps. So pump is the heart of our hydronic system. And with pumps, we need to know two values. First one is flow rate. So this is what we are designing or what we are pushing in our systems. Usually it's liter per minute, liter per hour, cubic meter per second per hour, different values. For me, the easiest is with liter per minute, but depending on manufacturers, you will see different values. This is one thing. Another thing is head or pressure drop. Usually kilopascals, meter head, millibars, and so on. Let's say we'll say kilopascals. And the pump, at the beginning, if we have zero flow rate, this is maximum pressure on our pump. So our pump can deliver, let's say here, 70 kilopascal of pressure drop through our installation with this pump. If our flow rate is maximum, let's say 40 liters per minute in this case, our pump is without pressure. So we cannot push anything. And if you connect these 2 points, you will have pump characteristic. So this is characteristic of pump, how we are increasing the flow rate. Our pump needs to push more, let's say, electricity to rotate on the higher point. And we have some duty point here. I will now try to open whiteboard just to draw something. You'll probably see. So here is the whiteboard. And here you can see pump characteristic. So this is pump characteristic. What is important? It is important that, let's say, we have duty point here. So duty point. What is the duty point? It is the intersection between our system and our pump curve. So this is our system. So this is system. Because when we are pushing more flows, we are increasing the pressure. And at some point, let's say, here is 40 liters per minute. This is the duty point of the pump. So intersection between pump curve and, let's say, here is 40 kilopascal. So this is important. So how we are choosing components, what we will see soon, will affect how our pump is working. And usually in modern heat pump systems in EU, you will have all modulating pumps. In UK, still you can have some fixed speed pumps. So if you have fixed speed pumps, you will have something like this. So this will be three main curves. So let's say 1, 2, and 3, and you can choose between these three curves. If you let me just try to put a different color. If you have modulating pumps, which is always recommendation, but depending on countries and what is inside of the heat pump, in modulating pump, your curves will be all the way here. So pump will adapt the flow rate depending what is your system characteristics. So if your system, let's say if your flow rate is here on some, let's say mild day, let's say here we have 15 liters per minute, your pump will maybe work like this. And maybe your system characteristic will be like this, depending on the system. But generally, this is what we are trying to understand and trying to make with our heating system. So pumps really wide topic, but just want to make introduction for Nigel and what we will explain here. Let me now share again. You will not see a whiteboard. So pump duty point. And before Nigel start, I want to make this topic also water volume and water flow rate. So these are the two most important things when we are dealing with heat pumps. We have, generally speaking, depending on manufacturer, so please check with your manufacturer, but depending on manufacturers, you will have minimum flow rate around 7 liters per minute for one fan unit, so up to 9 kilowatt, let's say. And for two fan units from 9 to 16, you will have 12 liters per minute. But this is minimum flow rate, so below that, you'll have flow error. We want to have nominal flow rate, so we want flow rate available higher than that, but just for you to know what is minimum. And also what you will see that minimum water volume is 5 liters per kilowatt. So for example, if you have 10 kilowatt unit, you need 50 liters minimum, but this is minimum for defrost and for some other things. But what we want is 15 to 20 liters per kilowatt. So this is ideal water volume. Our pump, because of the compressor, we need more volume. We need volume for some of important things, what I will mention soon. And also you need to know that we have pump inside. Always recommendation to go with this pump directly, without separation and without anything else. But our heat pump is stupid. So what we are pushing here on return, on this sensor, this is what we will have back from our heat pump. So what we are pushing here and what we are going here. So this delta T and other things, this is theoretical. So we need to make everything perfect so our system will work really good. Why is water volume and flow rate important? First part, you will see usually compressor short cycling. So it's usually fine, it's okay. We have short cycling on high outdoor temperatures, on autumn, on spring. But if we have in deep winter short cycling, it's not good. What is short cycling? When our compressor starts here and then stop. Start, stop. This is short cycling. So if we have, let's say, 5 to 10 starts per hour, what is maximum, we want modulation. So here is, let's say, 0. We want our compressor to modulate from 20% to 100% all the way down, because we want our compressor warm and we are spending always the most of the energy on startups. Second part, refrigerant condensing temperature. This is maybe too much for people here because we are focusing on hydronics, but just for you to understand, with gas boiler or with pellets, we have fuel, we are burning on 1000 degrees and that's it. Here, we are not creating heat, we are moving heat, and we are moving heat from our evaporator, compressor, condenser, and expansion valve. This is why we need to keep this condensing temperature really, really good. If we have low water volume, our condensing temperature will go really high and then go down. So this is a second reason why we need water volume. Third part, probably most important, is defrost. When we have high humidity in the air, you can have ice here, and then our heat pump needs to reverse cycle to go in cooling to heat outdoor unit, and we need water volume or capacity. We need capacity so we can have in 10 minutes, 5 to 10 minutes, defrost cycle done. And the last part, delta T. So I mentioned we have theoretical value of delta T5, but depending on our flow rate, on our volume, we will have real delta T. It is 1, 2, 3, or 10, or 15, depending on our volume and our flow rate. So 5 is theoretical, ideal, what we want to achieve. but really depends on water volume and flow rate. I think I'm good. 20 minutes, more or less introduction with general concepts. It's short time, but just for you to think about these topics when you are dealing with heat pumps. Now, Nigel will show you something from ESBE with focus on valves and on ESBE products. So Nigel, stage is yours.
Yeah, thank you very much, Mario. Hopefully you can see that. Can you confirm?
Yes.
I'm in slideshow?
Yes.
And I'll change my pointer to laser. So thank you very much for everyone for attending. That's me, Nigel Raper, Technical Manager for ESBE Ltd in the UK. We've only been set up as a subsidiary of ESBE for 1 year, but I'd encourage our UK viewers to contact us through the phone or the email that you see there if you have any issues in product selection or product configuration, you're struggling to set products up, because they're not more difficult to set up, but they can be slightly different to what you're used to. So I'd encourage you to make use of that technical helpline we have there. We can also offer in-person training or virtual training, really going into depths of it. Today, we're going to concentrate on mainly domestic products, and then with a slight tilt towards heat pump installations. So I thought I'd run through kind of the main components within a heat pump installation, and then we'll do a bit of a dive into ESBE valves and how they fit into it. So that installation there, I'll run through it, but not all ESBE products are on there. And likewise, we don't offer, for example, the strainer and the pressure reducing valve, but I'll run through that. So we have our heat source, which is the heat pump that Mario's talked to us earlier about. But beyond that heat pump, we have a pair of antifreeze valves outside of the building. And as we follow that hot water coming into the building, the first thing it meets is a diverter valve. What that diverter valve does is it diverts the names, the titles in the name. It diverts the water between either heat emitters, here we've got radiators and underfloor heating circuit, or if there's a demand for hot water, it heats the water up in the cylinder and then meets the return circuit back through a strainer. That's very important to protect the heat pump and maintain efficiency of the pipework. An expansion vessel back through another antifreeze valve and back to the heat pump. This side of the circuit is all hot water, where we've got a shower and a wash hand basin. And again, another expansion vessel and a pressure reducing valve to stop us overpressuring that cylinder and having the hot water too high pressure.
Nigel, we have one question, which is, let's say, usually people are questioning, do we need 2 antifreeze valves? Or maybe it's good to have one on the lowest point?
It's best practice to fit them in pairs, yes, because the hot water pipe can freeze as well as the cold water pipe, and there's not necessarily separation within the heat pump circuit. It's best practice and normal practice to fit 2 antifreeze valves.
Yes, because usually we are talking about protecting heat pumps, but we are also protecting pipes. So we don't want pipes also to be frozen.
Absolutely.
Thanks.
So brings us nicely onto the antifreeze valve. We're very proud that we launched our antifreeze valve in September this year. And I'll just talk a bit about antifreeze valves in general. So why do we fit them? We've already talked a little bit about it prevents damage. If the heat pump's turned off for any reason, whether that's a power cut or turned off for maintenance and not turned back on again overnight, it's low temperatures, the antifreeze valve prevents damage to the heat pump and the system and the pipework. Can I just put some antifreeze glycol solution in? You can, yeah, that's one solution. But the downside of that is that there's a lower heat capacity of the liquid. So glycol has a specific heat capacity which is lower than water. So for every litre of water, you can put more heat into it than you can into a litre of glycol. So, for example, the specific heat capacity of water is 4.2, I wrote it down, 4.2 joules per gram, but the specific heat capacity of a water glycol mix is around about 3.9. So you'd be losing approximately 10% efficiency by using a glycol mix. And again, glycol's difficult to use. You have to dispose of it carefully, maintain, monitor it. And the other thing is a glycol mix is harder to pump around the system. It's more viscous, so using energy to pump it around the system. So where do you put them? Now then, you put them outside the building, obviously, because that's where the danger of freezing is. We put them on both the flow and the return, and you fit them at the lowest points so that the water will drain out from that lowest point. So what do they do? Once the temperature, ours, opens up at 3 degrees, so once the temperature of it's on this, once the temperature of the fluid going through the pipe drops down to 3 degrees, it opens, allowing the fluid to escape. So that expansion that you naturally get when ice forms is not an issue because the liquid's got somewhere to escape out of this antifreeze valve. So how do they work? So this is a cross-section of the lower half of the ESBE antifreeze valve. So the blue arrows obviously are the water flowing through the pipe. This white area here is a capsule, and this is a wax element. You see wax elements in your radiator valves, your thermostatic radiator valves, your mixing valves, your thermostatic mixing valves used for blending water down, but we're using them in the antifreeze valve. And what this element does is, as the water gets hotter, it increases the volume of this wax in here. So the wax grows in size and pushes this white piston out of the wax element, pushes on this grey piston, and moves it into this region. But conversely, as the temperature drops, the wax shrinks and the spring pushes this grey piston, and you see it's through an O-ring housing here. So once the grey piston comes out of the O-ring, it allows the fluid to escape out of the bottom. So that's how a ESBE antifreeze valve works. Other manufacturers do it slightly differently, that their elements not directly in the water flowing path. So you're reliant on the water making its way down to the element. And theirs has a flat face seal, so it's got a sealing washer here. And as the element shrinks, it's reliant on that washer coming off its face. And we found that the piston seal is a much more reliable breaking of that seal rather than something that's had significant spring or water pressure on it for a long duration, might be several years, and you get a phenomenon of stiction where it's less likely that the rubber seal will become unseated. So we'll move on to diverting valves. You remember from the original schematic, it was the first point that the water hit. And I'll just talk a bit about different configurations of a diverting valve. So this is kind of a traditional sprung return diverting valve that you might be familiar with from gas installations, and they've been used many, many years in the UK, where we have the heat source coming in. I call this the branch, but always in from the middle. And then within here, and I'll show you a video of this, or actually we've got it live on the camera slightly later, but there's a rubber ball, and this almost swings like a pendulum by the motor from blocking off one port when you want the heating circuit and blocks off the other when you want the hot water circuit. Now, this is an ESBE motorized ball valve. So again, we've got the heat source coming in from the same point, but it actually has more a brass ball that's seated in there. and the ball has several ports drilled into it, and it's the rotation of the ball that allows the diverting the water from the heating to the domestic hot water circuit. Simple configuration, we have a rotary valve, and this has a rotary shoe that rotates around in the valve, again diverting water from, again it's coming in the same port and diverting it from the domestic to the heating circuits. Now they're all very similar with the same configuration. The confusion comes from people out in the marketplace because we have some valves which can be used as diverting valves, which have to be used in a different configuration. So the heat has to come in through one of the run ends, be it this one, or it can come in from this direction, and we're diverting it between the branch and the remaining run. So that's our VRG 130 range. We also have a VRG 330 range, which is a high flow version, and that's our highest performing valve for diverting because of really high flow rate and low resistance through the valve. I'm just going to try and do something different. We'll stop sharing that presentation.
Nigel, just one question. What is the main reason for, let's say, VRG 230? It's different, let's say, just regarding pressure drop. It's different inside of the body.
It
Just
is,
question
yes.
because from the outside, it's everything is the same. So I am now installing my heat pump and what to do. And sometimes it's easier to have, let's say, branch like this, and sometimes it's vice versa. So what is the main issue?
So one of them has an L-shaped shoe and one has a T-shaped shoe. So it can divert. The T-shaped shoe can divert around two corners on the 230 range. So it can go up and then to the left or to the right, whereas the 330 and the 130 has an L-shaped shoe, and it can only go straight through or to the left or to the right.
Okay, clear. So from outside, everything is the same. Inside is different.
Correct. Design. Yes. So I'll just switch to my camera. So this is the motorized ball valve, and I'll try and show the inside. And again, we struggled with focus the other day when we had a bit of a,
it's fine.
A trial with that.
Focus, but we can see the ball.
So you can see the ball.
Yes.
If I try and shine a light, we can see the small area that the water's coming through from one side and no water going through the other side. And then if I motor the valve, you'll see that very slowly that ball is cycling across and closes off that port. And then when I switch off the current, it opens that port back up. So that is a traditional diverting valve with the motor in there. Now, what we're seeing, what we're getting people are starting to use is the motorized ball valve. So this comes with a head, a motor on it. And again, we've got within there, hopefully we can get in focus, we have a ball, and we'll see that this port is open. See my finger coming through here, and the actuator rotates that ball and closes off that port and opens up that port. You'll see we have a much greater waterway with this style, and that's a motorized ball valve. The other style we were discussing earlier was our rotary valve. This is the rotary valve. Mario's just been fitting them this morning. And this, as the name suggests, rotates around. The red tick suggests which port's being blocked. So we see the port's being blocked there. Move it around here, and this port's being blocked here. But what's actually happening within the valve, I've got a section valve that's been cut open. So we actually have, if I try and rotate that so that you can see, we have a shoe in there that rotates. So I'm hoping you can see that as we rotate this, it opens and closes the port. And then in the fully open, in the straight through position, where there's a very good flow rate because of the full bore straight through that valve.
Nigel, maybe good point what I asked you about if you remove the cap, how will you know that your valve is
All right.
closed?
So
Yes,
if we remove this, if we remove the red indicator on this spindle here, probably not so good focus, but there's 3 splines on this spindle, and there's 1 spline missing with a small flat here. That always corresponds to the flat, to the blockage in the shoe, that part's blocked off. Thanks for that, Mario.
Yes, thanks.
Nice reminder. So I'll go back to the presentation. So that's a little bit about the different styles of diverting valve. So we'll talk a bit about KV and KVS. So what is KV and KVS? Everyone bands this term around. Technically, it's the flow rate of water in cubic meters per hour that passes through a valve with a pressure drop of 1 bar. What's that actually mean? If you have a valve and you've got a pump directly connected to it, that pump's running at 1 bar, 10 meters ahead. It's how much water will go through that in an hour. So the higher the value, the more water you get through within an hour. So the higher the value, the lower the resistance through the valve. So that's KV. So what is KVS? That's simply the KV value with the valve fully open. So that's KVS. People ban this term around KVS with not actually knowing what it means. All it is a measure of resistance. The higher the number, the lower the resistance through the valve.
Or maybe good analogy is, let's say, with if you have bigger hole or smaller one. So just for people to imagine what is the KVS. So if you have hole like this or like this, you can push. This is the KVS or KV.
Yeah, KVS, a big
KVS.
hole, lets more water through, yes. So what effect does that have? We're going to compare 2 ESBE products here that can be used for diverting. So our highest performing diverting valve, the 330 range, has the highest KVS. So we'll see the KVS, the ZRS range is 5.7. We're going to take a nominal flow rate of 30 litres a minute. That's typical 10 kilowatt heat pump flow rate. So our KVS on our 330 range straight through the valve is 17. And at the same flow rate of 30 litres a minute. Don't worry about the maths coming up. We're not going to quiz you on this later. But that results in a pressure drop through the valve at this flow rate of almost 10 kPa. Now, if we run the maths on the 330 range, you would imagine that because the KVS is 3 times higher than the KVS on this valve, that you're going to expect to be, well, a third of the pressure drop, maybe 3.3 kilopascals through it. No, that's not correct. Because of the mass, because we've got this square here, it's actually a 1/9 of the pressure drop. That shows why KVS is so important through these diverting valves. The effect of that is you have more flow rate going through it for a given pump pressure, which gives you a much more efficient system.
So yeah, I will just add initially this will decide if you need additional pump or no sometimes. Because this 10 kilopascal could be, especially on 30 liters per minute, this is like 10 kilowatt. This is the main thing. And also, Nigel put VRG 330. 130 looks the same, but with lower KVS. So
yeah, so the 130.
Try to choose 330. I think price difference is not an issue.
It's very similar. So the 130 has a KVS of 10. So it's a massive difference to go up to KVS of 17, and the price difference is very little. The other characteristic people often overlook on diverting valves is the actual differential pressure. I'll come on to what does that mean, but it's called differential pressure or shut off, and you'll see again we've got 3 different styles of diverting valves. And they've got very different differential pressure allowance, what it will work up to. So the maximum differential pressure is on this valve is 100 kilopascals, 200 kilopascals, and then over 3,000, but you would never work at that because it gets noisy. So we wouldn't recommend you use it above 200 kilopascals. But what does that actually mean? In the diagram here, we have a pump and we're diverting between the hot water cylinder and the heating circuit. So I'm saying the pump's working at Y. Mara, we were discussing this a couple of days ago, Mara, and you were saying that could be 1.5, 1.7 bar. So that's 150 or 170 kilopascals. And if you're concentrating on circulating through the heating circuit, and it's constantly circulating around that, the difference between the heating circuit and the dormant hot water circuit will be the allowable differential pressure. So you may have your pump running at 170 kPa, and it would and very little pressure here. So it would be outside the capability of some of the valves, and this is actually a decent value for a spring return valve. We see much lower figures on other manufacturers' spring return valves. So it's very important to understand these shut-off pressures to be compatible with certainly a heat pump system, which are running at much higher pressures. Just going to talk a little bit about mixing valves, and I'm a bit short on time now.
You're fine. I think you have a few minutes.
So there's two ways of mixing on a heating circuit. For example, take an underfloor heating circuit. You can put a thermostatic mixing valve in there, and you turn the dial to say 40 degrees. That's shown in the diagram or the image, and you set it, and it'll deliver 40 degrees for every day. That's roughly 40 degrees. These aren't always that accurate. We're only going to get plus or minus 3 degrees. Now, if a more advanced way of doing it is electronically, using a motor and a mixing valve, using one of our rotary valves with an actuator on top. The advantages of this is that you can have a variable mixed temperature. So what does that mean? So on a warm day, you can mix to a lower temperature. It's warm outside today, it's about 12 degrees here. So you would have your underfloor heating circuit at a much lower temperature and benefit from the efficiencies of that. It allows more efficient control, and it's much more accurate, this. So we're going to deliver maybe plus or minus half a degree rather than plus or minus 3 degrees that you'd see from the old style thermostatic mixing valves.
Thermostatic is maybe good for domestic hot water. If you have 60 degrees in your tank and you want to limit this on your tap, this is fine. But for underfloor heating, it's really poor.
It's an old technology, and you don't take the advantages of modern control systems. I'll talk a bit about valve authority. Here comes the sciencey bit. What's good valve authority? So this is a circuit here. We've got the mixing valve, and we've got the underfloor heating circuit. So good valve authority, a textbook good valve authority, is to match the pressure loss through this valve with the pressure loss through the underfloor heating circuit. Why do we need to do that? So this ensures that the full stroke, the full rotation of the valve will be used. It ensures controlled mixing. If you imagine you put a valve which is way too big in here, and you put a DN100 valve into a DN15 pipe, and you ask that valve to deliver a bit more heat, so it opens up and suddenly it will flood the system with hot water. The system will overheat and instantly shut down. That's an exaggerated example, but that's what you find, that the valve opens a little bit, suddenly finds it's overheating and closes instantly. And this results in hunting, a phenomenon where the valve's constantly adjusting. On the other side is, if this valve's too small, there's a danger that you couldn't get enough heat through it, and you're not achieving your design temperature, or you're pumping against unnecessary resistance. You'll see this in our catalogue.
Just to add, on diverting, we want the lowest resistance possible. But on mixing is another way. We need resistance so
Yes.
we can control. If we don't
So
have resistance here, we don't have mixing. So
so we
we need
have
resistance.
yeah, we do, to add control to the system.
Yes. For example, 330 will not maybe be too good for
Yeah,
underfloor, but for diverting is excellent.
correct. And 330 has an unequal mix between the two mixed ports, so it's much more difficult to achieve the desired mixed temperature. And we'll see on the in our catalog, you'll see, and this also confuses people. You see that for the one size mixing valve, DN15, there's 6 options of KVS, and this is quite daunting. Well, which one do I need? So I'm going to talk you through briefly, because we're running out of time, how to size the ESBE mixing valves. This looks even more daunting. So the easy way to look at it is this is the valve and this is your system. So on your system, you select the flow rate. So we'll say 0.1 litres a second, or we move along that to the valve. And this grey area is where we need the valve to be operating in. So we'll see there's 2 black lines intersecting. There's one which is a 1.6 kVS, and there's one which is a 1.0 kVS valve. So we know we can use either of those. It's best practice to choose the smallest kVS valve. So that's the more difficult way of doing it. But we do have an app. Everyone loves an app. And probably short on time, I was going to show it on camera, but basically you open the app up, select what your mixing valve is, type in your flow rate, your DT, and it suggests which valve you need to use. Final bit is actuator. People don't understand what style of actuator they need for each application.
Yes,
So I thought
we have few questions on the chat. So yeah, this is
okay, I'll hurry up then.
no,
Diverting.
no, this questions about this just
About the actuator
update.
selection.
Yeah.
Right, okay. So onto our rotary valves, we fit an actuator. And the actuator is just a motor. People call it a head. And for diverting operations, you either want it blocking one port fully or blocking the other port fully. So you need that full stroke of 90 degrees. It never needs to be midway. It always needs to be either in one position or the other. In the spring return valve, it's either on or off. You apply a current and it's one port, you remove the current and it's the other port. On these 2 valves, they have 2-point actuators. Not to be confused with 2-port, it is 2-point. That's why I quite exaggerate that term, which means the actuator can sit in 2 points. So when you're buying a head for a rotary valve, it's important for diverting to select a 2-point actuator. And on mixing, we have 3-point, which allows us to hold the valve in any position throughout its stroke. We supply a current on one cable to rotate it clockwise and a current on the other cable to rotate it anti-clockwise, so the control system can hold it at any mixed point. And finally, we've got a proportional control. So we have a supply voltage onto the actuator, and then we have a separate controlling voltage. Often it's anywhere between 0 and 10 volts. So 5 volts, for example, would hold it 45 degrees mixing from both ports. So I thought it was a good idea just to give a basic overview of which actuator are suitable for which application, because that does confuse people. We get people on the phone saying, I've got a 3-port valve or a 3-point valve. It's just a distinction on the actuator. Thank you very much for your attention. Once again, rather than struggling on, please phone us up, email us, just get in contact. That's what we're here for. Thank you.
But just 1 minute, what we are doing currently. So currently, I started the new online educational platform, and first course is live, so it's refrigerant cycle and basics. But currently, we are preparing more advanced things like hydronics, valves, buffers, and so on. Here, I will just put you. You will have here little bit of overview what is inside. So, interactive assessments. So this is like first course. You need to drag and drop. There will be in hydronics part everything about valves, pumps, buffers. This will be interesting topic. You can scan QR code here and go to the website, but just we try to make it simple to have one topic, 5 to 10 minutes assessment, and that's it. So from science of learning, it is important to have focused lecture. So this is like short overview. You can find more videos on YouTube channel. And
Just
also I put
to vouch for that, Mario, I completed the first module and I thought it was excellent. I retained the knowledge because of the format you put together with the interactive tutorials and the quizzes at the end. I thought it was an excellent format.
Thanks. Yeah, feedback is from currently experienced guys, new guys. We are trying to target everyone because even like, let's say, Nigel, you have 20, 30 years of experience and you find you useful. This is what I'm trying to explain to people. We want to cover everything so everyone can retain knowledge because it's huge area. So to try to make it simple. And here I put now this one course is live, so €150. You have 10% discount with code SB10 until end of November, so 30th of November. So it's around €135 or 115 pounds. This is first course, Introduction to Technology, so basics, refrigerant cycle and physics. In preparation is heat pump design, so heat loss, pipe sizing, radiator sander for heating, hydronics masterclass, valves, pumps, buffers, everything related to hydronics, installation and commissioning, and maintenance and troubleshooting. So soon, beginning of the year, the plan is to make everything more than 100 videos. So follow us, please, and I will send you an email with more details how to stay in touch, and check the website if you need. Thank you one more time.
Thank you very much for everyone for attending.
Thanks, Nigel, and thanks ESBE team for collaboration, and hope we will have more things like this soon. Thank you,
Mario.
Thanks very much.